Hi, welcome to week 3 of Science 30. This week we're going to be talking about fields, and we're specifically going to be talking about electric and gravitational fields. Now, there are 3 types of fields that we're going to talk about in Science 30. This week we're going to talk about electric fields and gravitational fields, and next week we're going to talk about magnetic fields. Now, fields explain how forces interact over a distance. We know that if we were to take a ball and throw it up in the air, it will fall to Earth. We know that if we were to have 2 oppositely charged particles, they would be attracted to each other over a distance. Same with 2 ends of a magnet. Now, in between those 2 objects, we don't see anything. And that's what fields do. So fields express the space between those charged particles or things with mass or those magnets, and gives the points of space in between a value. And so by knowing those values, we know what's going to happen between those objects. Now, electric fields are what exists around anything with a charge, and gravitational fields exist around anything with mass. And those are the 2 types of fields that we're going to talk about this week. So now electric fields. Electric fields are defined. So the way that we define these electric fields are with a positive test charge. Now, a positive test charge is an imaginary thing, but it's a positively charged particle. So if we were to take a positively charged particle and put it next to this positively charged thing, it would be repelled and would go away. If I were to take a positively charged particle and put it around a negatively charged particle, it would be attracted to it. So that's how we define electric fields. If electric fields can also interact. If I have a positively charged particle and a negatively charged particle, we know that they're going to be attracted to each other. So the electric field around these things would look something like this. Now, the direction of the electric field is again where a positively charged particle would go. So it would go towards the negative, and it would go away from the positively charged particle. We can also have maybe 2 negative charges. These are going to repel each other. So their electric field lines are not going to attract each other. They're going to be repelling each other. Now again, the direction is where a positive test charge would go, so it would go towards that negatively charged particle. But those charges are going to repel, so their field lines look a little bit different. A gravitational field is anything with mass. Now, Einstein went a little bit further and actually expressed this as indentations in the fabric of space-time. If you think about it as like a bed, if you were to put like a heavy bowling ball in the middle of the bed and you were to put other things around, it would roll towards where that indentation is. That's kind of how we explain gravity using Einstein's ideas. However, gravitational field theory works pretty good for on the surface of the Earth. And now this is around anything with mass. So if I were to put an object here, maybe outside of the Earth, the gravitational field would pull it towards the Earth. It is still a circular field, just like the electric fields. However, because the Earth is so large, on the Earth, it just appears to be pretty much a straight, uniform field, because we don't really ever get that far from the center of it. Now, in your data booklet, we have 2 formulas that we're going to use to look at gravitational fields and electric fields, and you'll notice some similarities. If I were to take the electric field and graph it as a function of distance, or I were to take the gravitational field and graph it as a function of distance, in both these relationships, those are inverse squared relationships. So as I get further away, the force or the field gets weaker. And that should kind of make sense. There is a gravitational field and a gravitational force felt on me from like Jupiter. However, because Jupiter is so far away, that gravitational force is so small. There's also a direct relationship with the mass and the charge. So if I were to plot electric field as a function of the mass, or if I were to plot as a function of charge, or I were to plot gravitational field as a function of mass, those would be direct relationships. So if something gets more massive, the gravitational field around it goes up. As something gets more charge, the electric field around it goes up. Now, one thing that is different are these constants. So the electric field formula has what's called Coulomb's constant. You'll notice this is a relatively big number, 8.99 times 10 to the 9, whereas the gravitational field formula has this constant, 6.67 times 10 to the negative 11. K is a lot bigger than G, and that really gets at the fact that the electromagnetic force or electric fields are usually a lot stronger than gravitational forces or gravitational fields. It depends on what it's around. But on Earth, the force of electromagnetism is a stronger force than the force of gravity. At your K again, it's in units of newtons, meters, and it has units of, go to your formula sheet, it's on there. So the mass of the Earth is 5.98 times 10 to the 24. You'll notice that it is less than the Earth and way less than the Sun, some other number. So let's look at some of these formulas. So this one first asks for the electric field strength, 30 centimeters from the center of the balloon. So this is a negatively charged balloon. If we want to look at the direction of the electric field, again, a positive test charge would go towards it. It would be attracted. So the electric field around this balloon would look something like this. Now I want to find the electric field at a point 30 centimeters away. So maybe this is 30 centimeters. I want to find the electric field at that point. So my formula is electric field is KQ over R squared. Now when we are doing this calculation, if you look at Coulombs, that's what we want to do for these calculations as well. So K is 8.99 times 10 to the 9 newtons times meters squared over Coulomb squared. Q is my charge. Now nano is 10 to the negative 9. So this is 4.5 times 10 to the 9, negative 9 Coulomb. So it's a very small number. One thing you'll note, I didn't worry about the charge here. The charge is really important for determining the direction of the electric field, but we don't need it for determining the magnitude of the field. We could kind of put absolute values around that if we want. So the negatives, positives don't really matter in this calculation. And this is 30 centimeters, which is 30 times 10 to the negative 2 meters. And I need to remember that that's squared. So I type all this in my calculator, and I get 450 newtons per Coulomb. If you look at kind of what the units are doing here, I have one of these meters, actually two of these meters, that's meters squared, so meters squared. I have one of these coulombs, and so I have newtons per Coulomb. That's the unit for electric field. Which, if other thing to keep in mind, here we have a question dealing with the International Space Station and looking at the gravitational field strength experienced by the astronauts in the ISS. This is a good question because there are some misconceptions here with kind of what an orbit is and what weightlessness is. So here's the Earth. If I look at the space station, so here's the space station here. The space station is only about 470 kilometers. So that's 470 times 10 to the 3 meters. Now, if I want to find gravitational field strength, okay, so big G, M over R squared. The M is the mass of the thing causing the gravitational field. And so this is the Earth. So it's big G times the mass of the Earth. Mind is when we're talking about the radius, this is the distance to the center. So the satellite is 470 kilometers above the Earth, but this radius of the Earth is important as well. So the r that I need to use here is this entire distance. So the height plus the radius of the Earth. That's how far it's going to be from the center. So when I talk about this total r, so the radius of the Earth plus the height of the satellite, it should be 6.84 times 10 to the 36, and then that's squared as well. So big G, 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24, divided by the height above the center of the Earth squared, and I get 8.53 meters per second squared. Now this is interesting because on the surface of the Earth, gravitational field strength is 9.81 meters per second squared. So as I get higher from the center of the Earth, it should go down, right? As I get further away, the gravitational field strength will decrease. Like on Everest, the gravitational field strength will be less than at sea level. In the space station, you'll notice they still experience pretty significant gravity. Like on the moon, it's 1.6. In the space station, it's fairly high. Now, what an orbit is, this kind of gets at the misconception because gravity there is actually pretty significant. It's only 470 kilometers above. But what satellites do in the space station is they have a very large velocity and they're moving very quickly. So they are actually falling to the Earth. But because a satellite is moving so fast, by the time it falls to the Earth is moved out of the way. And that's what an orbit is. So the space station is actually constantly falling, and the astronauts inside are constantly falling as well. It's just before they hit the Earth is moved out of the way, and so they continuously fall in an orbit. That's the same as that with the mic. One more question here that you can try, kind of as a challenge question, or maybe pause it, answer this question. Okay, so this question, again, is dealing with gravitational field strength. Here you'll notice it has a different unit of newtons per second squared. So it's equivalent to the same thing. So that's big G times the mass over r squared. Gives me the radius, gives me the gravitational field strength, and it wants to find the mass of Mercury. G is a constant, it's never going to change. So if I rearrange this, I need to multiply by r squared. So G times r squared is equal to big G times the mass divided by G will allow me to find the mass of Mercury. So G is my gravitational field strength of 3.7 times r squared. So this is a really big number, 2,439,000. And I need to remember that that's squared, divided by big G, which is 6.67 times 10 to the negative 11. I do that calculation, and I get 3.30 times 10 to the 23 kilograms. If we were to compete. So that's this week, dealing with gravitational and electric fields and their formulas, which are similar, but dealing with different things.